Our next lesson is about dividing right triangles into subtriangles. At the top of this page, there's an image of a right triangle with the altitude drawn in. And there are not one, not two, but three triangles in that image. There's a small triangle, there is a medium-sized triangle, that's the big one, and the medium-sized triangle. So there are three triangles in that, the left one, the right one, and the big one, and we'll talk today about how those three triangles are related. Now here it says we're doing one CCRSM standard, but actually this standard will actually be hit in the next lesson, but that proof uses this idea, and so I want to hit this in a separate video, and then we'll apply it next lesson in proving the Pythagorean theorem using similar triangles. Let's get started. We're in lesson 21 today, and I know that last video was lesson 22 and 23, but we're going to go back because to me these ideas are so connected with the Pythagorean theorem that I wanted to do it right before the Pythagorean theorem. And we're actually going to start down here with example 1. Recall that an altitude of a triangle is a perpendicular line segment from a vertex to the line determined by the opposite side. So BD is an altitude of this right triangle. In triangle ABC to the right, BD is the altitude from vertex B to the line containing segment AC. How many triangles do you see in the figure? Well, we just talked about that there are three. B says, identify the three triangles by name. Now, I want you to practice writing them, but using the correct correspondence. So I'll start with triangle ABC, and that is going over what I'll call the short side, the short leg, to the long leg, and this is the hypotenuse. So it's ABC. The order goes over A to B, over the short leg, B to C, then over the long leg. So I will name the others in the exact same correspondence. So the middle triangle, this one, again, I go over short leg, then long leg, would be BDC. And the big, oops, I've already done the big triangle. Now the little triangle, this triangle down here, again, we're short and then over the longer leg. So then triangle ADB are the three triangles that we see in this image. Now the next question in C, we want to consider the altitude of a right triangle from the right angle to the hypotenuse. The altitude of a right triangle splits the triangle into two right triangles, each which share a common acute angle with the original triangle. In triangle ABC, the altitude BD divides the right triangle into two subtriangles, triangle BDC and triangle ADB. Now in C, it asks, is triangle ABC similar to triangle BDC? Well, let's look at this. ABC is the big triangle, and BDC is this medium triangle. Again, we've written the correspondence to be correct. Now, they both have a right angle. So angle D in the red triangle and angle B in the green triangle are both right angles. And they both share angle C, which is congruent to itself by the reflexive property. And so triangle ABC is similar to triangle BDC by the angle-angle similarity criteria. Next, we're looking at is triangle ABC, which again is the big triangle. Is that similar to triangle ADB? Well, again, we have a right triangle. So angle B in the big triangle and angle D in the little triangle are both right angles. And this time we have angle A that is the same in both triangles. And angle A is congruent to itself by the reflexive property. So again, triangle ABC is congruent to triangle ADB by the angle-angle similarity criteria. All right, now this image right here is not in yours. I copied it over so that I could look at it. Now is triangle ABC similar to triangle DBC? Well, again, we're looking at the correspondence. ABC is going over short, then over long leg. Is that similar to triangle DBE? C, D, B, C. And the answer is no. No, because segment BC does not correspond with segment BC. That this BC doesn't correspond with this BC, that we didn't have the right correspondence. And so that order of the letters is really, really important. E says triangle ABC is similar to triangle BDC, and triangle ABC is similar to triangle ADB. That was from letter C we did earlier. Can we conclude that triangle BDC is similar to triangle ADB? And the answer would be yes. There is a sequence of rigid motions and dilations that map triangle ABC onto both triangle BDC and triangle ADB. So there would also be a sequence of rigid motions and dilations that map triangle BDC to triangle ADB. In essence, you can take the sequence of rigid motions from BDC and take them backwards onto ABD, and then the rigid motions and dilations from ABC onto ADB. Anyway, it'll work because they're both similar to each other. Okay, in F, we're looking at a different right triangle with some different angles, but the point is that the similarity will still hold in any right triangle. So the altitude in this triangle is segment GH. In letter G, we're asked to find the three subtriangles that are all similar so that the correspondence angles match up. So I'll start with angle EFG. Now this time in those letters I'm going across the hypotenuse and then short leg. So that is similar to triangle. Well, I've not proved that they're similar yet. And then I have hypotenuse for the medium triangle. Let's see here, medium triangle, hypotenuse, then short leg would be triangle EGH. And then for the small one, I have hypotenuse and then short leg. So triangle GFH. Those have the correct correspondence. H, does the altitude divide triangle EFG into two similar subtriangles as the altitude did with triangle ABC? And the answer is yes, by the angle-angle criteria. Again, we have each pair of triangles has the right triangle, the right angle, and then one other angle that's reflexive. And so for every pair of triangles, you have the angle-angle similarity criteria. In example 2, we're using those subtriangles to find some missing lengths. And we're first asked to draw the altitude BD, so I'm dropping this down perpendicular and calling this point D. And then I'm labeling AD X, and I'll label DC as Z. So 13 is the whole length, and the length D to C is is Y. And B to D is Z. Now we're asked to find the values of X, Y, and Z. And because these three triangles are all similar to each other, I can use some proportions to figure out these three lengths. Now the first step is to redraw these three triangles so it's easy for us to see the correspondence. Okay, here I've drawn, it's big triangle, medium triangle, little triangle, which isn't that big of a difference, but I should have drawn it a little more extreme than that. And it is a little tricky to figure out where the letters go and where the numbers go. But if you think it through, as far as I look at the right angle first and get that letter there, and then I look at the short, along the short line and along the long leg, and then they're filling in the missing sides. Okay, so first I will look for angle, I look for segment X. Okay, now this triangle over here, the big triangle, is the one that I have to use because I know all three lengths in that triangle. So X corresponds with 5. And then I'll use the length in the small triangle, the same triangle as X, that I know. I know this is 5, and so that corresponds with this 13. And this is a right to left equals right to left ratio. And I can solve this proportion. X times 13 is 13x. 5 times 5 is 25. If I divide by 13, I find that x is equal to 1.923. Similarly, we can find angle y, and y corresponds, again, I'm going back to this triangle because I know all 3 lengths in the big triangle. Y corresponds with 12. This is, again, a right to left ratio. And in this triangle, I know this is 12, and 12 corresponds with 13. Again, it's a right to left ratio, right to left ratio, and I cross multiply to find y. And so y is equal to 11.077. Now I could find z as well using the exact same method of z corresponds with 5 and then looking within that triangle, the 12 and the 13. I'm not going to go through and do that for space and for time, but hopefully you can see how we can look at these similar triangles to find missing links, and we'll practice this more during class. This lesson was about dividing right triangles into subtriangles. The point of this lesson is that those 3 triangles are similar to each other, and so we can write those similarity statements, and we can also find missing lengths using proportions. Thank you for watching.